since we have a little 4x4x4 region here of potentials that we are calculating, we go ahead and read a bigger set of grid charges, in fact an 8x8x8 set of grid charges, and then we slide a window that's the 4x4x4 window across this small block, incrementally across this bigger block. And for each of those, then this requires just one particular weight from that stencil in constant memory to go ahead and all of the threads can use that, because all of these pairwise distances here between, you know, my block that I'm calculating for and my block of data in shared memory, these are the same at each of these shifts. And so this is just the approach that we devised to go ahead and use constant memory the way that it's best suited. Okay, so these developments for the GPU version of multi-level summation method for molecular dynamics, this is quite new, and so I have just a very small set of initial results to show you. This short-range force kernel that I showed you has not been extensively optimized yet, and yet I'm heartened by the fact that when I go ahead and just do, you know, a simple test case here, and I'm only testing on a single CPU and then a CPU with a GPU, and I'm testing against the NAMD GPU code, that the performance is a little bit better right now with both with calculating energies, which the NAMD code doesn't do yet, but also with something that's, you know, relatively new and not very well tuned.
Are the forces computed roughly with the same precision?
Well, I would argue that my forces are being calculated. Well, the NAMD light forces are being calculated to. I mean, it's all single precision, but I'm not doing any force lookup tables here in this calculation. So in that sense, I have more accurate forces. Do I need them for good molecular dynamics? You know, that's an open question.
I think that the answer would be that yours would be easier to adapt. If you needed double precision for doing some of these simulations with huge structures, hundreds of millions of atoms, then the precision may become more of a concern because of the forces involved and things like that, or if you're doing weird structures or weird compounds, then it would be easy. A kernel that's based purely on arithmetic, all you're doing is changing the floating point type to improve the precision in a very targeted way. But if you have a lookup table-based kernel like the existing NAMD kernel, if you wanted to increase the precision of that lookup table, you may have less flexibility, because that may mean that you need more entries in the table, but you have a fixed size on-chip GPU shared memory, or maybe you needed higher precision numbers in those tables. Again, changing the size of the table of memory, that is going to be one of the things that is much harder to adjust. For something that uses a lookup table, you're probably going to end up being stuck with what you've got. If you have the ability to do the same thing or read with a similar degree of efficiency, do it with pure arithmetic, that code will be much easier to tweak to give you better precision or better performance just by changing the floating point types in a few key areas. So really in force calculations, the main area where you lose precision is when you sum those forces together during the accumulation step. So if you want to improve precision, that would be the first place you would add double precision or compensated summation. And so in a kernel like Dave's, it's likely to be much easier to do those things there than to have to rearrange all those tables.
So how do you compare, how do you debug your code? I mean, you have a kind of a golden solution
computed by direct summation or something like that? By looking at all pairwise interactions or something like that?
Well,
and then you look at the difference of MSM versus that, and then PME versus that.
yeah, I mean, yeah, you're asking about how I would debug something like MSM, and so I've already done some quite a bit of extensive testing on MSM alone. Where you do experiments where you increase the cutoff distance, you decrease the grid spacing that you're using, and making sure that things are converging correctly up to whatever order of accuracy that you expect, based on the interpolation, the order of interpolation that you're doing. So I've already done that type of testing on MSM, so I already have those results that I can test and have tested the GPU MSM against.
Right. I guess basically what I'm saying is that it might happen that you need a somewhat finer grid for the MSM to get the same kind of accuracy as you need for a PME for a coarser mesh. So those numbers.
Oh, actually, it's just the opposite that's true. MSM actually has a much it takes a much coarser mesh than PME does. So, but yeah.
One thing I'm surprised is on your MSM results, you notice that the CPU only, the short takes 8 times longer, whereas the GPU only takes 1.5.
Well, this relates to this trade-off between doing arithmetic versus the lookup table.
This is where the lookup table is really winning here.
This is why NAMD always did the lookup table approach, or in recent history, maybe not always, but recently, a long time. That's why Jim put the lookup table in there in the first place, because doing the math on the CPU, that was a losing idea because it was already CPU arithmetic bound. So using the lookup table makes some of that arithmetic go away. But on the GPU, it's a win. It's better to do arithmetic and avoid the lookup tables. So that's what you're really seeing is, in effect, Dave is unwittingly, he's demonstrating the difference between the two hardware architectures. One prefers lookup tables and is cache, basically lookup tables equate to cache, right? So CPUs, they don't have much in the way of arithmetic, but boy, do they have a lot of cache. These new CPUs have megabytes of cache. That's so much cache that even multi-million atom simulations almost fit entirely in cache. That's crazy.
Yeah, their parallels doesn't, but
yeah, the parallels doesn't, but the coordinates do. And so that just demonstrates how well suited that approach is to the existing CPUs. Now, as CPUs get to have maybe 30 cores or something like that, the amount of cache per core will start to drop, and they start to become more GPU-like because they'll have more arithmetic if they have AVX and they can do 8-wide SIMD calculations at a time. Then one of these GPU algorithms will probably be the way to go for future CPUs. But for older CPUs, the way that the existing NAMD works is the better way. So you can just see the difference in
another
approach.
positive, if you want to put a little footnote, is they're included because
That's the
CPUs
way
are moving.
they're heading in the same direction. It's just that they are an order of magnitude lower number of cores, but it's inevitable. They won't have a choice. We can't raise the clock rate anymore. In fact, clock rates are going down. The per core performance is actually going to be lower in the coming years, especially once a larger fraction of commercial applications are heavily multi-threaded. The CPU vendors will then aggressively go towards increasing number of cores and decreasing clock speeds because of power consumption and ultimate performance. The only design space that the engineers have to work with is the number of transistors. Everything else they're pretty much boxed in on. They can only decrease the other numbers. But the number of transistors, they get a free lunch every 18 months. So this is how you get that speed.
yeah, I was going to ask you something later time, but kind of interesting to think about what's the future architecture going to be for high performance computing. And so as they increase the number of cores in CPUs, how is that going to affect the amount of cache that's available?
It's going to go down.
So
it's also going to, I have heard that the average amount of system memory per core is now near its peak, and as we go forward, the number of cores will be increasing much faster than the total system memory capacity. And the theoretical number I've heard thrown about is that in the end game, we will end up with a ratio of about 1 gigabyte of system memory per CPU core, regardless of machine size. That's where things are heading. So that also tells you about, in order to use large memory problems, you're going to have to use parallel approaches even on the CPU, because that's the memory that they'll have to work with. So it's interesting.
I'd actually expect the amount of like level 1 and maybe even level 2 cache per core to stay about the same, because the number of cores on a chip is being driven by feature size shrinks.
Right.
And the same feature size shrinks lets you put more memory. So if there's a balance between cache and execution units, they should be able to maintain that.
Yeah.
But, you can only have a shared cache between so many different individual cores. You might start seeing additional levels of shared cache even within the same socket.
So it becomes a game for them to push the pieces around the board and say, well, how many cores do we want versus how much cache per core? It depends on what kinds of applications you're trying to run. A lot of HPC applications end up being memory bound anyway. Like all those LinPack benchmarks, they are cache blocking, but ultimately it's memory bandwidth and MPI bandwidth that dominate the overall machine performance. And there are many codes which the cache doesn't help at all. These guys that do ocean modeling codes, they hated the transition from the big Cray vector machines to the modern cache-based machines, because their codes, instead of being 90% efficient in terms of the peak rate of the hardware, they went from 90% efficiency on those old machines to running at about 5% efficiency on modern machines. So those guys would rather it be the other way around. So they have codes that are inherently more GPU throughput-oriented codes. Yeah.
So I'm going to stop here unless there are more questions. Yeah.
Have you guys thought about or analyzed or threw out the idea, instead of using MSM for long-range electrostatics, like fast multiple method?
That's how we used to do long-range electrostatics back in the day.
The problem that we have with fast multipole method is that it calculates discontinuous potentials and forces, and this is inherently bad for molecular dynamics.
Okay, so you have if you hit this discontinuity, you may get like a big force that's sort of a result of the grading.
Right. So the issue was the reason we were initially doing a form of fast multipole back in the mid-90s, and we switched PME because PME produces smooth forces that are of sufficient accuracy, and to get the same degree of energy conservation with fast multipole, we had to crank up the accuracy much higher than we actually needed for the simulations.
For time-stepping purposes.
Right.
So we did that.
And also fast multipole can't do periodic boundary conditions, right?
There are
I think there are
versions
Oh,
of
okay.
that.
So it's like you had to do the expansions in higher order.
Yeah.
Right,
Get
just
back.
because
It's sort of
when
like-
you jump between
Okay.
cells.
To quash those discontinuities.
Yeah,
Ba-
okay. So then you were
basically,
doing more work with the expansion and you are just calculating.
You eventually see the discontinuities creep in to heat up your system, even if you're calculating, near machine precision. So that's the problem.
I think we're going to do these out of order since you guys,
Yeah.
unless you want to stay all day.
No, I'm ready to go.
Okay. Let's go ahead and set up right now. Any other questions for Dave while Andrew gets going? I think we're going to skip my talk for now on radial distribution functions and go straight into Andrew's talk, because he's just here for part of the day today. And I will just find a time to fit this in, either in the early part of the afternoon or after a break or something. Mine's much shorter anyway. So.